Hi everyone, and welcome to our video, our first video actually under Unit 6, which is titled Differential Equations and Mathematical Modeling. And our first lesson here, I'll go over this in pink, the notes, the title is Solving Differential Equations and Initial Value Problems. So we're going to get right into it, and just know that this is going to be a bit of a review from Unit 4, where we did antiderivatives. We learned how to anti-differentiate. It'll be a little bit of a review with that, with a little bit of new stuff sprinkled in. So let's take a look at this first paragraph. It says, an equation like, and I'm going to highlight this, an equation like dy dx equals 3x squared plus 1 is called a differential equation, because it contains a derivative. So that should look familiar from your math past. When we find all the functions y, so when we solve a differential equation for y that satisfy the differential equation, we have solved the differential equation. So in other words, anytime you're presented with a derivative, dy dx equals something, and you solve it back for y, you're solving a differential equation. So let's do that now. So if you look here, we've got the same problem, dy dx equals 3x squared plus 1. Okay, so the first thing you want to do when solving a differential equation is you want to get all of your x's, I usually take them to the right, and all of your y's to the left. So I'm going to start by multiplying both sides of this differential equation by dx, and that will allow me to clear the dx's from the left-hand side, and I'll just be left with dy equals 3x squared plus 1 dx. Now, if we anti-differentiate or find the indefinite integral of both sides, what's going to end up happening is we're going to integrate with respect to y here, and we're going to get a y, because essentially there's a 1 right here. So the antiderivative of 1 with respect to y is just y, because the derivative of y is just 1 going backwards. So y equals, and now on this side we'll anti-differentiate. We're going to add 1 to the 2 to get a 3. And when you divide 3 by 3, you get 1 plus the antiderivative of 1 with respect to x is just x. And now, what am I forgetting here? Hopefully your brain is thinking, Miss Callahan, where's the plus c? I like to add the plus c over here on the right side. Now, technically, and I'll do this in pencil so that I can erase it, I would have actually added a c to this side as well. Y plus c equals x cubed plus x plus c. But when I solve for y, what'll end up happening is I'll just be moving this c over to join this c, and that can just be lumped together into one big plus c, a constant. So don't worry about adding the c on both sides. Just go ahead and add it to the right side so that y is alone. So that's it. That's the first part. Y equals x cubed plus x plus c. Now, let's move on. Now suppose we are given what's called an initial condition. An initial condition is the value of y for one value of x, aka an ordered pair that is on this graph. Using this information, we can solve the initial value problem. So up here, when you just had dy dx equals 3x squared plus 1, that was considered a differential equation, an equation that represents a derivative. When you have a differential equation, but tagged on the back is a y value at a particular x value, this is called an initial value problem. So to solve the initial value problem, you just take what you did up here and you go a step further and you solve for c. So we already know this part. We've already done this above, so I'm not going to redo it. I'm just going to write what I have here. Y is equal to x cubed plus x plus c. That's the differential equation solved for y. Now I'll plug in the initial value. So y is 4 when the x's are 1. And what that's going to allow me to do is solve for the particular c. So let's see, this is going to give me 2. If I subtract 2 from 4, I get 2. So my c is 2. So my final answer is y equals x cubed plus x plus 2. So I'll box that in as my final answer. And that's it. It's that simple. Okay, let's go down here to example 1. It says solve the initial value problem, very similar to above. We're not breaking it into parts though. We'll do both parts in this space. So we start with dy dx equals 2x minus 1. So let's start by getting the x's to the right. So I'll multiply both sides by dx. Okay, canceling those out. So dy is equal to 2x minus 1 dx. Now I'm going to anti-differentiate both sides of the equation. This is going to give me y equals x squared minus x plus c. And I'm going through that pretty quickly because we've already learned how to anti-differentiate in a previous unit. Okay, now let's solve for c using the initial condition here. So y of 2 equals 0. That means when x is 2, y is 0. So I'm going to plug those in and solve for c. So I'm going to have 0 equals 2 plus c. So c will have to be negative 2. So my final answer to example 1 is nothing more than y equals x squared minus x minus 2. Pretty simple. Let's go to example 2. Solve the initial value problem. Okay, same idea. So we start, just as we did before, by multiplying dx, both sides, cancel. dy is equal to secant squared x dx. Okay, integrate, integrate. So we have y equals. Now, this causes me to pause because I have to think about this. It's trigonometry, which marches to the beat of a different drum than your simple polynomial. So I have to think, what function's derivative is secant squared x? Now that's a pretty simple one because that's one we straight up memorized in a previous unit. So hopefully you're thinking, or even if you had to look it up, that it's tangent x plus c, because the derivative of tangent x is secant squared x. Okay, now we'll fill in our initial value here. So when x is pi over 4, y is negative 1. So negative 1 equals the tangent at pi over 4 plus c. Now we're appealing to our unit circle. So negative 1 equals. The tangent at pi over 4 is actually 1. Because when you take root 2 over 2 divided by root 2 over 2, you get 1. And solving for c, we're going to get minus 2. So my final answer to this problem, y equals tangent x minus 2. So we're just cruising on through. Let's flip it over. Just 3 more to go. Example 3. Just another problem. Solve the initial value problem. dy dt. So I'm switching up the variables a little bit here. The derivative of y with respect to t is 2e to the negative t. And my initial condition here is y of the ln of 2 equals 0. Okay, so this time I'm just going to multiply both sides by dt. Cancel those out. dy is equal to 2e to the negative t with respect to t. And now I will integrate both sides. So I get y equals. Now what I like to do over here is, since I have a constant 2, I'm going to pull that 2 to the front of the indefinite integral so that I can focus more on what's inside here. Now this one's interesting because I know that if this was a positive t, the antiderivative of e to the t is itself e to the t. So I think this is going to be fairly easy. It's just that this negative has to come into play. So let me think about this, and you think about it too. You can even put me on pause here. to think about what this would be, you have to just play with it to think, well, what would I put here so that the derivative would give me back this? Well, if I just put e to the negative t, I know it's not going to be that because the derivative of e to the negative t would be e to the negative t times negative 1. So since I don't want that negative 1, I will compensate here with a negative, and that should do it, and then add my c. So in my next step, I'll take this negative and I'll pull it to the front of the 2. So y equals negative 2 e to the negative t plus c. Now, if you're not sure about that, my process I just went through, let me just show you how this works. So if I take the derivative of this, I should get back my original here before I ever anti-differentiated. So just using a quick product rule, I'm just going to run a quick check so that you're okay. So my check would be, let me change colors here. I would take the first, which is negative 2, times the derivative of the second, which would be e to the negative t times negative 1, e to the u du dt. And then, so that's first derivative of second plus second times 0, which is the derivative of negative 2. So this part goes away, and you can see right here, the negative 2 times the negative 1 makes positive 2 e to the negative t, which is what we started with. So we're good. Okay, now all we have to do to finish it is plug in our value here. So when x is, or when t is the natural log of 2, y is 0. So 0 equals negative 2e to the negative natural log of 2 plus c. And this part right here, I'm just going to put in my calculator. So I've got negative 2 e to the negative ln of 2, and that's giving me negative 1. So that's negative 1 plus c. So my c is going to be 1. So my final answer to example 3 is, I'm going to write it up here, y equals negative 2 e to the negative t plus 1. So that one was a little bit more difficult because we brought in e, a little bit more difficult than the problems on the front perhaps. Okay, 2 to go, and these are very similar. Example 4 says, the velocity v equals derivative of s with respect to t, which we learned in a previous unit, or acceleration a equals the derivative of velocity with respect to time, of a body moving along a coordinate line is given. Find the body's position s at time t. So that's what we're really looking for, position at time t. So we're going to use this idea of differential equations to solve this. So look at part A. It's giving me velocity as sine of pi t, and it's giving me an initial value here, s of 1 equals 0. So the first thing I'm going to do is rewrite v as the derivative of s with respect to t. And I'll set that equal to sine of pi t. Once I have that, I can multiply both sides by dt so that I have ds equals the sine of pi t dt. I will integrate, and voila, s equals. See, that's what I'm after. I want to find s at time t. Now here I sit anti-differentiating the sine of pi t. I think I'm going to need u substitution here because it's not just the sine of t. So I'm going to come off to the side and do some u substitution. So I'm going to let u be equal to pi t, this part. Then the derivative of u with respect to t is just pi. I'm going to multiply both sides by dt. So I have du equals pi dt. And I'm going to solve for dt by dividing both sides by pi. So I'm going to bring this information back over. So I'm going to have the antiderivative of the sine of u times dt, which is right here, du over pi. Okay, I'm going to come clear around here and keep going. I am going to think of this pi on the bottom here as being 1 over pi. So I'm going to bring that to the front. S equals 1 over pi as a constant, antiderivative of the sine of u du. And now it gets pretty easy. I know that the antiderivative of sine is negative cosine, and I'll add that c. The derivative of cosine would be negative sine, but there's no negative here, so I have to compensate here so that the negative times the negative sign makes the positive sign. Okay, I'm going to put the negative in the front, so negative 1 over pi cosine of, let's go back to what u was, pi t, plus c. And last but not least, I will find c by using my initial value. So when t is 1, when t is 1, s is 0. So 0 equals negative 1 over pi cosine of pi times 1 plus c. That will give me, well, the cosine at pi is negative 1. So this is going to give me positive 1 over pi, but when I subtract it to the other side, negative 1 over pi. So my final answer, to this problem is S equals negative 1 over pi cosine of pi t minus 1 over pi. Final answer. Okay, and our last one, part B. This time they're giving us not a velocity, but rather an acceleration. So our acceleration is the constant 32. So the first step is I'm going to write acceleration as derivative of v with respect to t. I'm going to multiply both sides by dt, so that dv is equal to 32 dt. I am going to anti-differentiate both sides to give me v equals 32t plus c. Now I'm going to use one of my conditions up here. They're telling me that v of 0 equals 20, so I'll put 20 in for v, 0 in for t, and I see that my c is 20. So velocity equals 32t plus 20. Now I'm going to rewrite v, because remember, I need to find s. Let's not forget what they wanted. They wanted s. I'm going to rewrite v as the derivative of position with respect to time. I'm going to multiply both sides by dt to give me ds equals 32t plus 20 dt. I'm going to anti-differentiate both sides. So s equals 16t squared plus 20t plus c. And then I'm going to use my other condition, s of 0 equals 0. And you can see that if this is 0 and these are zeros for the time, then c is just going to equal 0. So my final answer for s is 16t squared plus 20t. Final answer. So that is how you solve not only a differential equation, but also an initial value problem. Thanks for watching.